So, a very good morning to all of our attendees. My name is Vidish, and on behalf of Midas IT, I'd like to extend a very warm welcome to each and every one of you to today's webinar session on cable stayed bridges modeling and analysis. So, without further ado, let's get started. So, these are the contents of today's presentation. I'll first talk a little bit about our company Midas IT and our software Midas Civil. Then we'll get into the crux of today's web session, and I'll talk about the modeling and analysis philosophies for cable stayed bridges, wherein we will discuss such things as the initial pretension or form finding for cable bridges, construction stage analysis philosophies, and other related topics. And finally, we will touch briefly upon the second and third order effects in cable stayed bridges. So first, about Midas IT. Midas programs were being developed since 1989 and have been commercially used since 1996. Our headquarters is in Seoul, South Korea, and we currently have corporate offices in Beijing, Singapore, Shanghai, Detroit, Dallas, Europe, India, and Japan, and of course we are ever expanding. We are also currently one of the largest civil analysis software developers in the world, with a proven reliability of over 5,000 project applications, an intensive quality control system, and of course our analysis have been verified by various institutions all over the world. So what is Midas Civil? Well, Midas Civil is a 3D finite element based package that is geared towards bridge engineers, but is by no means limited to bridge engineers. It is a general purpose product that can be used to create even models of structures like plant structures, tanks, silos, dams, tunnels, and many other such models. So even a geotechnical engineer can find some use for modeling and analyzing in Midas Civil itself. But of course, it is geared towards bridge engineers, and specific design functions are available for the bridge models only. So what type of bridges can Midas Civil handle? Well, it can handle quite easily the conventional bridge types like culvert, slab bridge, or girder bridge. It can even take care of the stage segmental bridges like balanced cantilever bridge, precast segmentally constructed bridge, the full staging method construction for bridges. So each of these construction methods can be easily dealt with in Midas Civil. And finally, Midas Civil is also very adept at handling cable stayed, suspension, or extra dose bridges. So coming now to the modeling philosophy. First, I'll talk a little bit about the initial sizing. So aside from loadings, the pylon and deck geometry as well as the orientation are driven simultaneously by cost as well as by aesthetics. So normally the loadings only play a part in finding the section dimensions. However, the orientation and the overall shape of the bridge is driven usually by the aesthetic requirements. So now coming on to the span length, or more importantly the ratio of side span to the main span. So this ratio is determined by the backstay forces in the side spans, and the backstay forces are maximum when the live load is on the main span, and it is also the lowest when the live load is on the side spans. So the backstays usually get the largest stress variation among all cables, and therefore the span lengths have to be have to be kept such that this variation does not exceed the fatigue strength of the steel material used in the cables. So this particular graph that I'm showing you is from Jim Singh and Georgiakis in 2011, where they investigated the relationship between the ratio of the side span and the main span, which they've plotted on the vertical axis, to the ratio between the live load and the dead load, which they've plotted on the horizontal axis. The value of zeta that you see just above the curves is the ratio between the absolute minimum backstay force to the absolute maximum backstay force. So Next we'll move on to initial modeling, and here there are three main modeling methods. So first we have the spine beam model, we have the multi-scale model, and we have the meshed finite element model. So first let me talk about spine beam modeling. This is the most common modeling method, wherein the bridge is modeled using beam and truss elements and links that represent the bearings, and deck section itself can be modeled using equivalent section properties. So the deck element, you need not actually go for the entire geometry for the deck. Equivalent section properties are more often sufficient. Now, particularly with respect to cables, since the cables themselves are inherently nonlinear, the cables are usually modeled as tension trusses, with the sag effect considered through the Ernst formula that you see over here. So this is the basic Ernst formula, that is wherein the stiffness of the cable is related inversely to its horizontal length and directly to the axial stiffness, the axial force. Now this graph here, so you can see here the variation of the effective stiffness of a stay cable to the horizontally projected length, which is a relation which is related to its total overall length as well. So as you can see, for the same amount of axial stress, the longer the cable, the lesser will be its stiffness because of the more pronounced effects of sag. Coming on to multi-scale modeling. So in multi-scale modeling, we basically make use of different elements for creating a unified model of the bridge. So a combination of beam elements, beam, plate, and solid elements is used. And this type of modeling is more advantageous in that it can capture more accurate and localized results. However, in creating such models, one has to be careful and mindful of the different degrees of freedom for the different elements. So the interconnectivity between the beam, the plate, and the solid elements has to be carefully considered due to the differences in the degrees of freedom. And finally, we come to the meshed finite element modeling. So this is perhaps the most realistic modeling of all, and it gives more realistic structural responses and with an accurate representation of local and global responses. But this is usually quite cumbersome to model an entire bridge, so only certain critical portions are modeled and analyzed. So in this image that you see on your slides, this is an image of a saddle clamp for the cables that were used in the Bonny River Bridge in Nigeria. This particular model was created using our advanced finite element software, Midas FEA. And finally, let me talk a little bit about the support systems for conventional bridges. So this particular slide shows the 6 common support systems that are used frequently for conventional cable stayed bridges. In each of these support systems, you will notice that the deck is allowed to move laterally in one way or another, while most of the systems utilize the expansion joints at the ends. Many others utilize, for example, the case for D and E. You will notice that the expansion joint is provided at intermediate points. So it really depends on the site conditions, on the cost, and the aesthetics considerations on what kind of support system the engineer would like to provide for his or her particular project. So now, before moving on with the presentation, let me switch over to the software and show you how a particular cable stayed model can be made in our software Midas Civil. So this is the interface of Midas Civil, and I'll open up the cable stayed bridge wizard. So this is the wizard itself, and now I'll begin the model. First I'll import the material and section properties from a pre-existing model file. So here I'm importing the material properties from the model file that I had already created beforehand, and now I'm doing the same for the section properties. So here now I have all my section and material properties. The section types I have used as value type over here, and here in these dialog boxes I can specify the dimensions and the for the cables, the spacing for the cables, and also I can specify the shape of the deck. So here let me enter an initial slope of I'll say 5% and a total arc length of let's say 220 meters. So if I want to see how the model looks, I can just click here, update and draw, and it will show me how the model looks. Furthermore, if I want to have my bridge as asymmetric, I can choose between the options. For now, let me just click OK, and my model is prepared. Now what I'll do is I'll create a copy of this particular model on its side. So going to elements, translate. I'm going to create a copy 15 meters apart. And now that I have my copy, I'll just go ahead and activate the deck parts and hide away the rest of the model. So I'm doing this to create the cross beams. I'll just simply extrude elements from these particular nodes to create my cross beams. So I'm selecting the cross girder material and the cross girder section property. So with this, my cross beams have been prepared, and now I can go ahead and make modifications to the rest of my model. For example, let me activate the pier parts, and now if I want to create cross member elements at the pier locations, I can simply do so in this fashion. So with this, the model is it's more or less complete at this point. You can make more modifications to it as well. But for now, let me get back to the presentation. So let me now talk about the analysis philosophy. So this is the basic philosophy or the basic workflow when creating and analyzing a model for cable stay bridge. So first of all, we find the value of cable tension that will give the optimum deck profile for the final model. This is also known as the initial form finding or pretension value of the ideal state of the cable bridge. Once we have found this initial pretension, we do a backward construction stage analysis to find the cable forces during erection. So in the backward analysis, we start with a completed model and keep on removing elements one by one in an order reverse to that of the original construction staging, and finally we get the member forces within the cable elements, which are basically the erection forces that we need. The third step is usually a forward analysis for checking the final pretension values and also for considering the time dependent effects, and finally we do checks with seismic, wind and other effects. So for the initial cable force finding, there are three basic methods: the continuous beam method, the bending moment envelope method, and the influence matrix method. So let me first talk about the continuous beam method. So in this particular method, the points of connectivity between the cable and the deck are idealized as pin supports, and we find the reaction are at each and every one of these supports. From these reactions we directly get the cable forces. So this method has some advantages in that the stackable location, this basically helps eliminate creep in the vertical direction at nodal locations and also gives a very uniform displacement profile. Now, the bending moment envelope method was one suggested by Swenson in his book Cable Stayed Bridges, 40 Years of Experience Worldwide. In his book, he mentions that the continuous beam method is not the best method for steel deck cable stayed bridges from the economic standpoint. Now, normally when using the continuous beam method, you only apply the initial loading as dead loads. We do not initially consider the live loads. The live loads are later on added once the initial pretensions have been found. They are later added in the form of an envelope. As you can see from this particular slide, the image before you, in the figure B, this is what the profile that we would normally get if we consider the continuous beam method, as it were. But Swenson suggests that from an economic standpoint, we should consider the bending moment profile as that in part C. So this particular bending moment profile can be achieved after tuning the cable forces such that the bending moment profile in the deck is as low as it can be, or as within the lowest permissible limits. So obviously this particular method would definitely give more economic more economic deck properties. However, at the same time, because we are increasing the amount of pretension in the cables, this will directly mean a higher amount of cable material needs to be used, and therefore for this particular method the cost of the deck has to be compared with the cost of the cables arising from the increased amount of pretensioning. And finally, we have the influence matrix method, or as it is known in Midas Civil, the unknown load factor method. So in the influence matrix method, basically we have a matrix of influence coefficients that are made to reflect the effect of loading in one or more cables on the rest of the structure. So any loading in one cable is obviously going to affect the entire structure. So this particular matrix reflects that behavior, and furthermore this matrix can be modified to accommodate different types of constraints, like you can have displacements, you can have reaction forces, you can have moment profiles and influence coefficients, and those particular influence coefficients can then be directly used. Furthermore, this particular method can and has been modified to incorporate a range of values. So for example, if you do not want to give exact values but rather a range of values, so even that can be done using the influence matrix method, in which case an optimization technique has to be used to arrive at the most optimal solution. And finally, once you have found your initial pretension values from any of the three methods, it may happen that these pretension values are not exactly falling within the desirable range for that particular material. So the cable forces may need to be tuned slightly, and in this case Midas Civil provides the cable force tuning option, wherein a user can directly tune the cables manually and see what effects that tuning will have on the entire structure. So let me now switch over to the software and show you these particular features. So let me open up a pre-existing model file. Now this particular model has already been analyzed, and as you can see on the left side in the works tree, as you can see, there are a lot of load cases that have been added, and many of these load cases are pretension load cases, and let me show you. As you can see, each of these pretension values has a value of 1 kilonewton only. So basically we are just using the unit load method. Now let me show you some results. Let me show you the bending moment diagram for the combined case, that is self weight plus the unit pretension loadings. So here this is the bending moment profile that you get for the self weight load case combined with the load case for unit pretensions in all cable members. As you can see, at the midspan we have quite a lot of bending moment, and quite a lot of it at the pier locations as well. Now let me go over to the unknown load factor method, or the unknown load factor function, and let me show you. So this is the unknown load factor function in Midas Civil. So here I have selected all of the pretension values that are required to be unknown. So as you can see, the self weight and additional loadings are already known, so their factor is 1, whereas the unknown load factor is to be applied only on the cable pretension points. Up next we have the constraints. So as you can see, there are several constraints, node 25, 27 and so on. So each of these constraints is a displacement constraint, wherein it has been assigned with an inequality. So we have an upper bound and a lower bound. So with this, Midas will calculate and find the optimal solution within these particular range of values. So let me get the unknown load factors, and here you see the load factors that are to be applied to the pretension values. So these are the particular load factors that are needed for the ideal state. Now if you want to check the influence matrix, you can even do that. So as you can see here, this is the influence matrix for this particular cable bridge model, and if you want, you can even create an Excel sheet. Let me show you. So this is the Excel sheet that is created and has the influence matrix values. So all the influence coefficients are there, and furthermore this Excel sheet has the equations written into it. So let me show you. So here you can see these are the equations that are written into it. So for example, if I modify any value, automatically the other values get affected. So this is something that can be easily added to one's project report. Now let me just create a new load combination for this. Let's say modified, and now let me close it. Let me now show you the results for the modified load combination with the modified cable pretension values, and immediately you will notice that the bending moment profile has changed drastically. So as you can see, the deck moments seem to have reduced quite a lot, and the value of the bending moment itself has also reduced. So this was using the displacement constraint. Of course, one can apply other forms of constraints as well, depending on the requirement. Now, first let me create a structure group, and the reason I'm doing this will become clear shortly when I show you the cable force tuning option. So I'm just going to add the entire deck portion in my deck structure group, and now let me go over to the cable force tuning option. So this is the cable force tuning dialog box. Here let me select my load case as modified, and let me create a case or a group for my deck moments, and I'm going to choose my, the beam force, and as soon as I add it, I get the moment profile within my deck. So this is the moment profile in the deck group, and here I can modify the cable pretension in real time and observe its effect, or the effect of the change in pretension values upon the entire model. So as you can see, as I am modifying the cable pretension, the graph changes according to the influence matrix. So this is particularly useful if one wants to observe the effects of rounding off, since in the field it is rather hard to give exact decimal point pretension values. One may need to round values off. So here you can simply observe the final effect of this particular activity. So once you have finalized your forces, you can simply upgrade them to the present model, and it will ask you to delete the analysis results. And now when you check on the pretension values, I'll be going to the tables, so they will not be unit values now, but rather the modified values that have been tuned using the cable force tuning option. So now let me get back to the presentation. So coming on to construction staging. So in case of cable stayed bridges, we normally have two kinds of construction stage analyses. First is the backward analysis, which is used to find the cable forces during erection. Now this does not account for the time dependent effects. And secondly, we have the forward analysis, which is used usually to confirm the backward analysis results when creep and shrinkage are not considered. And of course it can account for the time dependent effects as well. Now this particular slide shows the basic iteration process. So as you can see from the slide, the basic workflow is what we have followed thus far. We go for an initial cable pretension analysis, then this is basically the final stage analysis, and from here on we go over to construction staging, wherein we verify the member forces and tune the cable forces as required. And one final analysis has to be done with construction staging, considering the camber. So first of all, let me shift over to the software and show you the construction staging methods in Midas Civil. So this is the model of the backward analysis. Let me show you the progression of this model through the different stages. So at the first stage we have the final model, and in subsequent stages we begin to remove the cable segment by segment until finally we reach the point where there are no cables installed. So here this is the progression in the model, and I'll just switch over to the final stage, wherein you can see there are no cables installed. Now in order to find the erection forces, we need to find the member forces within the cables at the time of erection. So here let me switch over to truss forces, and let me start off with the last stage, that is CS30. This is the stage at which the first cable was installed, and this is the value of the cable force that needs to be entered for this particular cable. Similarly, the value for the other cable, as you can see from here. Then for the third cable installation forces can also be directed from here, and in a similar fashion for the other cables. Now let's talk about lack of fit force. When a segment is added to a bridge model during construction staging, that segment undergoes some deflection. This deflection changes the member forces in the cables, and during backward analysis we extract this changed cable member force information and use it as external pretension for forward analysis. Midas Civil has a feature called lack of fit force, which essentially calculates the amount of force needed to push the deflected segment back to the ideal state position. Thus, in effect, this feature removes the necessity of backward analysis, since the lack of fit force results can directly be added to the initial pretension force after analysis, and the same model can then be reanalyzed. So what this means is, basically, if you use the lack of fit force function, you need not do a backward construction stage analysis. So let me shift over to Midas Civil and show you how this can be done. So in this new model that I've opened, I will demonstrate to you the lack of fit force feature. So first of all, under the construction stage analysis control, so here we have the initial tangent displacement for erected structures, and this is the lack of fit force activation. So from here this feature gets activated, and here I have already described a structure group called lack of fit force. Let me go ahead and show you what are the elements under this particular group. So here you can very clearly see that the elements are basically all the cables in this model and some parts of the deck, as well as the key segment. So basically wherever the portion the jacking up needs to be done, those parts have been included in this particular group. Now let me show you the results of the lack of fit force analysis. So here these are the results for the cables, and as you can see, Midas gives you very detailed results on what is the actual lack of fit force and what is the summation of these lack of fit forces with the initial pretension values. So you can directly use these values for the forward analysis. Now similarly, we also have lack of fit force values for the deck sections. So here, as you can see, we have the lack of fit force. These are the deck section, these are the key segment deck sections, and as you can see, the program gives very detailed values on how much. Now coming on to Camber calculation. So Camber calculation is one of the many requirements for cable stayed bridges, and in fact it is one for nearly all kinds of bridges. For cable stayed bridges it is particularly important because the cable forces are very sensitive to the deflections, and therefore it is the engineer's prerogative to achieve as close to the ideal state once the construction is done as possible. So this particular slide shows the calculation of construction camber in Midas Civil. So the net displacement that is shown by the deflected shape that is shown by Midas Civil by default is that of the construction camber itself, and Midas can also show you the manufacturing camber that is shown as the real displacement, which is activated upon using the initial tangent displacement option. So let me shift over to the software and let me show you this feature. So let me show you the camber calculation in Midas. So first I will add a structure group, and now let me calculate the camber value. So I'm calculating for the summation load case. So here you can see this is the general manufacture camber across the different nodal points of the deck, and this is the construction camber. So you can even get the camber value in tabular format. So again, choosing the summation load case. So here this is the tabular values at different nodal points. Now let's discuss nonlinear effects. So there are three major nonlinear effects to be considered in cable bridges. First is the sag effect of cables. The second is the P delta effect or the second order effect, and third being large deformation or third order effects. So first, coming to the sag effects. As I had already mentioned before, for linear analysis, the cable element is treated as an equivalent truss with the effective stiffness given by the Ernst formula. But for nonlinear analysis, the cable element is usually transformed into an elastic catenary element that you can see on the slides as it is formulated based on the equations you see on the slide before you, and its stiffness matrix here is one that also considers its geometric stiffness. Coming to the second order effects. So for second order effects, now for the short to medium span bridge deflections, since they are quite small, so the second order effects can be limited to the live load effects only. What this basically means is that the initial pre-stress calculations and the dead load themselves, they can be done considering only the first order effects, while the P delta effect needs to be taken only when the live load is considered. Now for long span bridges, however, these should be considered for both construction and for final stage calculations, and particularly so because the second order effects can even affect the ideal state itself. And finally, coming on to third order effects. So for a very long span bridge, the large deformation analysis may indeed need to be done. So this is usually done by analyzing it using the geometric nonlinear analysis, and this figure that I have pasted on the slide is one for a very famous analysis method, the Newton-Raphson method for geometric nonlinear. So regarding P delta nonlinear analysis in Midas Civil, you can activate these features from the construction stage analysis control, and here you get different options. So depending on your requirement, you can do a complete nonlinear analysis, or you can do an analysis considering P delta effects only. So if you consider the nonlinear analysis, if you consider the P delta analysis only, you will get options for controlling the iterations and the convergence criteria. And if on the other hand you decide to go for a nonlinear analysis, you will get the option to choose between the independent stage and the accumulative stage. Now about the independent stage, so this is used for backward analysis, wherein the previous stage should not affect the results of the current stage. So if you're going backwards through time, the previous stage would actually be the stage ahead in real construction. Now coming to for accumulative stage, this is the one that is used in case of forward analysis, wherein the previous stage does affect the current stage. So right now let me show you selecting P delta analysis, and these are basically, this is a different file that I have opened, wherein the results file has already been analyzed and together with P delta effect, so the results will reflect the P delta effect as well. So all the member forces, for example, the member forces for the cables, etc. So now let me also show you one feature called the cable efficiency feature. So with this particular feature, you can directly get a measure of how efficiently a cable is acting, and the cable efficiency is basically a measure of its current utilized stiffness to that of its total material stiffness. So with this particular feature, with this result, you can very easily check on how much stiffness is being utilized for each and every cable. Analysis. Now one question that may come to you is what is the cutoff? When should we use linear, when should we use p delta, and when should we use nonlinear analysis? So in general, there are no hard and fast rules to decide when a third order theory should really be used. For the most part, engineers agree that the second order effects are quite sufficient. However, for short span bridges, Groglu and others have suggested that the dead load distribution be first analyzed as first order, and second order checks be done only for live load computation, as I had mentioned before. Furthermore, Wang and others have suggested that for main spans beyond 600 meters, third order theory is recommended. So again, this is just few researches that I have cited here. Other researchers may have other opinions, other engineers may have different opinions depending on their experience. So it really all boils down to what is the engineer's opinion based on his or her particular project. And finally, let me talk very briefly about some project applications of cable stayed bridges that have utilized Midas Civil. So here we have the Ironton-Russell Bridge in the USA. It was analyzed for construction stage analysis with time-dependent effects using unknown load factor analysis, eigenvalue analysis, thermal analysis, and vehicular load optimizations. The Weirton-Steubenville Bridge, again in the USA. Here we have the TU Delft train structure and traction project in the Netherlands, and it was analyzed for consideration of time history analysis. The Korabinli-Farvacha Bridge in St. Petersburg, Russia, again for vehicular load optimizations and eigenvalue analysis. The Lazarevsky Bridge, St. Petersburg. The Incheon Second Bridge, which is currently the 5th longest cable stayed bridge in the world. It was designed by Soyoung Engineering and Chodai Company Limited, and it was analyzed for construction stage analysis with time-dependent effects, geometric nonlinear analysis, and vehicle load optimizations. We have also the Stonecutters Bridge, which is the 3rd longest cable stayed bridge in the world, with a main span of over a kilometer long. This was designed by Arup and partners, and it was analyzed for geometric nonlinearity, thermal analysis, buckling analysis, eigenvalue, and construction stage with time-dependent effects. And lastly, but not least, we have the Sutong Bridge, which is the 2nd largest cable stayed bridge in the world today, and with its main span of again over a kilometer long, just about 70 meters more than the Stonecutters Bridge. It was also analyzed for similar effects as that for the Stonecutters Bridge. So thank you very much for having attended this web session. We hope you enjoyed it, and if you have any queries now, you may type them into the questions box, and I would be more than happy to reply to them.